wherever you are. Today, the agenda is three things. The first one is Severin is going to present analysis of the NeuralPixel targeting strategy so that we can deploy it on our pipeline. And then Nicholas agreed to present some statistical power analysis that he did that is complementary to what Lucas did last week. And then I finalized the first stimulus design, next version for SLAP2 data, and we are currently planning to run experiments this week, so I want to make sure that we have agreement on these. As usual, this meeting is recorded, and so we plan to release this on YouTube. So if you have any concern with us doing so, please let us know before at the end of the meeting, and we can adjust. Okay, thanks everyone. Severin, maybe you want to get started with your presentation?
Okay, 1 second. Do you see my window here, targeting area? Yeah.
We do. Yeah.
Okay, I'm gonna share at full screen. Okay, so today my goal of this presentation is for me to present you a little bit what we were thinking in terms of targeting and how we approach targeting in general with for our experiments. I looked at mostly at these two papers here that you can see, and basically they recorded from ACA. So that was an indication for me to just start with this. And I think we have Jordan with us today, so I'm looking forward to have his input on this also. From the community papers targeting area, that's what people have decided on. So that's V1, LM, M1, M2, PLIL, ACA, and RL and LGN. So I did my best to try to emulate this choice. So the strategy here is basically we make what we call the shield implant, which I will show you in a minute. We import it in a software called Pinpoint, where we have a CCF brain, and I will show you that also in a minute. And then we simulate all the probes insertions, and we have all the areas that it's supposed to be crossing. And then we do a surgery on a real pilot mouse. We test this on the rig. We get the feedback from this experiment. And then if at any point anything is wrong, we go back to the design of the shield implant and reiterate like this. And then at the end, we have a final shield implant, and we can insert it in surgery for the production mice and then start the production from there. So this is a shield implant. So it takes a whole hemisphere of the brain, basically. So the craniotomy is, as you can imagine, very big. Then the surgeon insert this type of implant that are 3D printed, and they are like the material is kind of a resin for 3D printing. So here is how we make them. Like we have this Onshape software, which is a software to make CAD drawings. And for example, here you have hole number 1. So all of these parameters here are for hole number 1. And you have, like, of course, the anterior posterior, the mediolateral, dorsal ventral. You have the angles of the probes. You have the diameter of each hole, etc. So once you know your coordinate, basically you can put a hole on that implant wherever you want. Then you import this in this Pinpoint software, which looks like this, and I will show you the real one in a second. So basically you import your implant, and it's on top of this CCF brain that you can use for targeting. And then basically just a reminder. So we have 6 probes. Each of them have a very fixed angle. We cannot change the angle. So that's why it's sometimes a little tricky to do the targeting, because we have like fixed angle. The probes cannot really cross each other. So it's a little bit tricky to do these kind of things.
Severin,
Yeah.
you have a question in the chat from Sarah?
Sorry, I don't see anything. So
Yeah.
yeah, let me know. Yeah.
What
What
is
is
the
it?
what is the purpose of the shield instead of doing multiple craniotomies?
Oh, well, the craniotomies are, we try to reduce the amount of craniotomies that we do, because, as you must know, you have always some damage. You always, and then usually you do also your craniotomy like the day before the experiment or the day of the experiment, which we try to avoid also, and we do that like a month before, so the animal can recover from it. But mostly it's like just to avoid to have an access everywhere, and to avoid like multiple craniotomies that can give like a lot of damage, basically. Okay, so let me show you now. Let me share. I stop sharing this. I want to share my pinpoint now. Okay, so here I'm describing you a little bit. Oh, and by the way, there's a whole paper on the shield implant that came out, I think, last year. If you're interested in like how all of this was tested and designed and everything. Anyway, so now we're on pinpoint. We have our shield implant here. On the left here, you have,
Question, can I,
yeah, yeah,
sorry, hi Severin, how are you? Yeah,
yeah.
so with this shield implant, sorry if I didn't get this, but is it like, I don't understand, still in each of these holes is a craniotomy, right?
So no, like you remove the bone, so you make a huge craniotomy on the whole
I
hemisphere,
see. So
and then
this replaces,
this
okay,
it's placed over, like the borders are placed over the skull,
I see.
and the middle is give access to the brain,
Yep, yep,
basically.
now I
And
understand.
and the
Okay.
holes are in the implant, not in the skull. Yeah.
And what is this shield made of?
So, some type of resin that you use for 3D printing. I don't know
Interesting.
exactly the name, but if you want the name, I can figure it out.
Yeah, don't worry. Thanks.
Yeah. So yeah, on the left here you have, so you have a color code for each probe, like let's say this green one here is in LM. So here are your insertions. So on the top right here you have the view, the coronal view, with like in red you have the channel that are recording, and so that's the view for this probe, the insertion for this probe. If I do for this one, you see there's another insertion. I can see that I'm crossing MOP and ACA. So here is a summary of the area that are crossed by each probe with the color code of each probe. You can add as many probe as you want. You can also add some different types of probes. Uh, Everything depends on what you want to do and where you want to go. So basically, here is the design that I'm proposing to you, and I'm going to go through it now. Okay, so I stopped sharing my. Do you have any question on pinpoint or?
Wait, so you guys do a structural MR of the mouse first to specifically define each one of these, or they're just generic?
No, we're taking a CCF brain, which is like a mean brain out of like 1,000 different brains, and
Okay.
it's what it's there. Yes.
Okay. Yeah.
That's why also that's a good point, because this is all theoretical, right? Like the brains are very different sometimes from that. And I mean, we've been very good at targeting, but like we should also expect some variation sometimes, and sometimes maybe some target won't be managed to be recorded from. So it's a it depends again about like how these areas are in individual mice, basically. But this is the best estimation we can do in terms of like, yes, seeing like which area we can cross with each probe.
Okay, that's cool.
Okay. So basically, the area to target, I used the list that you had in the paper. And my first question was which probe to use for ACA, MOS, IL, and PL, which I know that I can cross all this area with one probe. So I wanted to know if I can use probe A or probe F. So here are the simulation for probe A in the frontal hole there. And as you can see here, that's the crossing of this area. So you have MOS, ACA, PL, but it's very much at the border of this area, which is not the case if you look at F, because it's more angled toward medium, the medium brain. And so it just crosses better like MOS, ACA, PL, and ILA here. So I was thinking maybe to use F for this frontal hole. We used this hole before. That's why I'm using it, because I know that we can cross all these areas together with one probe. Now, okay, so I realized also from the papers that the coordinates that I used for this front hole and ACA is very different than the coordinates from the papers. So what I did is that I added another hole here with the coordinates from the paper to target ACA also. So basically that would give me, with probe A, we would have ACA. With B, we would have V1 here. With C, we would have LM here. D would go in RL, and D with RL goes through GLGN also. E would be in MOP here. And then we would have the frontal hole where we have like a lot of frontal areas.
Yeah, so how far anterior of bregma is hole A?
Let me check 1 second.
If you don't have
Actually,
any,
it would be helpful if you have the exact coordinates for these holes.
Yeah, I do. Let me 1 second. I do. I have all the coordinates. Let me share. So all the coordinates are here. So for example, this frontal hole here is my hole 6. So I can go to hole 6, and hole 6 is anterior posterior 2.7 instead of 0. I think it's 0.3 or 0.6. I don't remember in which direction. Anterior posterior is 0.3 in your paper.
okay, so this is all the way 2.7 of bregma?
Yeah, so that's this hole here. You see it, right? When I'm
Yes.
showing you. So that's a hole here when I can go through MOS, ACA, PL, IL. So that's the hole that I used. Now, nothing is set in stone. We can discuss everything. I just put this hole because I knew I could go through all these areas. But the hole you have in the papers is this one here that goes to ACA as well.
Okay, that's good. Yep.
So
Severin,
mhm.
there's a question from Sarah. Sarah
Yeah.
is, yeah, able to speak. In terms of
Okay.
PL, IL, ACA, I'm not entirely sure how critical the distinction are, and when based on EFIS, one can discriminate these areas. I think she's speaking about the ability to set boundaries between the areas
Yeah.
and so I think it's helpful you could speak to that.
That's very true. That's very true. And I think there's no good answer for that. Like we have now a software that helps us with most of the insertion, which is the IBL app for refinement of areas. But you're right. Like when we go through cortex and cortex and cortex, it's very difficult to have an area, delimitation of the areas. Usually, what we do is we trust the CCF brain, and then we detect where is the surface, and then we apply basically the CCF coordinates to this probe, which is the best we can do so far. You're right. Like this is tricky. Yeah.
Um,
Sorry, Jordan. So I was going to say, I have been documenting across different papers the coordinates, especially for regions like PFC, M2, like MOS. So if you want, I can share those. It's quite different when you go from one paper to the other, but I have just compiled some of these.
Yeah, the thing is that these areas are huge. So
Right.
if you guys prefer other coordinates than this super frontal one, or yes, let's discuss this. Let's work
I mean, in my
together to
document, I will share it. I have also the name of the authors, so the paper,
okay.
so we can see for what they've used it. But yeah,
Yeah,
I
okay.
will
Sounds
send it.
good.
Sure.
Sounds good. Yeah.
the I think these two insertions are going to be good. So we did independently. We did retrograde tracing of just retro T, tomato, and V1, and then looked across ACA how many neurons are projecting to V1. And it seems from our data that the maximum number of cells that project to V1 are about 0.5 anterior.
Mm-hmm.
We didn't look too far beyond 1.5 because it started to level out. So I think it's actually would be nice if you had a part of ACA that didn't have so many V1 projectors, and then a part that did, because you could make some comparisons. I mean, I can show you the plot if you want me to share it, but I don't want to derail anything here. But actually, I might be able to. I don't know if I can share an image in the chat.
I can I can stop sharing if you want.
I'll just it's like 1 second, just to show you what I mean here.
Yeah, let me stop sharing. Yeah.
Okay. All right. Am I sharing?
Yes.
Okay. It's this right here. Can you see this?
Yes.
Yeah. So we injected an V1 and then counted the number of soma, and then this 0 here is bregma. And you can see, that the number of we're just counting somas, but it's really in this first, let's say 75.75 millimeters that you have the most cell bodies. But still, if there are still ACA neurons all the way up at 1.5 and all the way back that are still projecting. So, I think what you have is going to be nice. This as long as you have both of those projections.
But the frontal one are way more than 1.5, right? So
Yeah,
and
2.7. Yeah.
yeah, and then and the hole for ACA that I added was at 0.3, so it's near from what you were saying.
Yeah. So the one you added will be right in our peak, which will be good. And the one that's up at 2.7, I think will add additional information. So I like what you have.
Okay.
But also, like, I'm talking to the Allen Institute here, and you guys have a lot more tracing data sets than I'll ever have. So
Yeah.
defer to you on that as well. That's just what I've seen. But also, we're only injecting in one central part of V1 and tracing. So there could be our distribution could actually reflect the retinotopy. So maybe there are more, like there may be some retinotopy along ACA. We don't know. So.
Yeah. Yeah. Actually, let me check, but you would even have a little bit, I don't know how that is possible, but like with the MOP hole, there is a little bit of ACA as well. So that would make you maybe 3 comparison together with ACA, which is cool.
Yeah, that's nice. I like that. And you could see different types of properties along that axis.
Yeah.
And
you have the dorsal and ventral as well. So
yeah.
No,
so,
I mean yeah. So oh yeah, so what we were just saying is that like now here I have this probe here, which is probe A, this probe that goes through the one I added at 0.3, and then with this angle I don't reach ACA, so I have to make a hole that is a bit more noise here. Sorry. Here, I have to push the hole a little bit towards. So maybe 0.5, what you were saying would work. Yeah. Do you see what I mean? Like here, the angle doesn't reach ACA here.
Yeah. So just some adjustments would be nice.
Yeah, just a little like more anterior hole. That's it. And then what else? Oh yeah, so we wanted maybe to leverage some things that we have here, some tools. So there are different probes that we can use. So there are one shank that I showed you before, and there is also some probe that have 4 shanks. And first we were thinking, maybe that would be interesting to use these 4 shanks for something in this project. So I was looking at the frontal hole again. I made it bigger so that the probe could enter here. And then on the right here, on the top right, again in red are the recording channels. And then here are the areas that it's crossing. So as you can see, basically, even if you use this 4 shank, you get only ACA and PL basically by you miss a lot of MOS. Like you cannot record deep basically because the channels are distributed over. It's the same number of channels than on the one shank, but it's distributed in the 4 shanks. So there is less span of channels. Yes, Alexander?
I'm wondering if it wouldn't make more sense to put 4 shanks in V1, since it's the back of the brain that has columnar organization, particular orientation columns, so we can see how they might interact. The other thing that might be nice about having 4 shanks is that you can move from 2-dimensional current source density CSD to 3D CSD.
Yeah.
And I don't think that will work in the front because you will need a lot of activation, in particular layer 4, a strong signal, in other words. And since we're working with visual stimuli, V1, there will probably get the best visual responses. So maybe we could have it both in the back and the front, but since we're not reaching maybe necessarily more areas in the front, might make sense to put it in the back.
My main concern with having a 4 shank is the other teams that use the 4 shank, they change angle every day so that they can distinguish the insertions at the end. We will have to do 4 days. So it means 4 insertions of 4 shank on the same hole, on the same angle, maybe with 2 different dyes, but still, that is going to be extremely difficult to annotate. So that's one point against the 4 shanks.
Well, I like the idea a lot. It would add a lot to what we
Mhm.
can do, especially with the data. Now, if you would do it in V1, maybe I don't know, maybe
Okay.
if it's considerable, but would the angle be tilted or would it be roughly perpendicular to cortex, to the surface?
No, they are all like tilted. Yeah.
Do you know how much tilt it is? Is it more than?
Yes. It's different
More
for
than,
each probe.
what about the back of the brain? Do you know roughly? Is it more than 25 degrees or?
I will have to look at.
It's okay. It's okay. Let me ask you this: in the non-shield neuropixels recording that you've been doing, was it also the case that the neuropixels were tilted with respect to the cortical surface, or back then when you didn't use the shield, did you always have?
They were exactly like this,
They were also tilted, right?
like all of it like this.
Yeah. Okay. So I'm asking because of the current source density, which I think is an interesting signal. And back then we also got good current source density, so it seems to be robust to a certain tilt. So that, long story short, that gets me. I would be very excited to have those 4-shank electrodes in V1, but I'm also a V1 researcher, so I'm biased. But, it makes more sense to me to put it in the back because the signal might become more interpretable if we go beyond spikes.
But my concern is very legitimate. Though, like, if we cannot annotate the probes, then there's no. You see what I mean?
I'm not concerned about that. I think there's a lot we could reconstruct. So if I know there's 4 electrodes, I could from the data find their geometry.
Oh, okay. Okay.
Yeah. So because there's a similarity relationship as a function of distance in cortex when it comes to local field potentials. You do multidimensional scaling, you should see exactly what the geometry of the electrodes was. So if we lack some annotation, I think there would still be rescue, but we could still find out these things.
Okay. Okay, so I can
I just want to it does seem like there's a lot of really interesting ideas, and I feel like maybe the discussion is going to continue. So
yeah.
it would be great if some of you just point on the discussion forum the pieces of information, and I think Severin can also share links with pinpoints and other things so that you can see the exact geometry. But yeah. I'm just saying, I feel like the discussion is going to continue.
I don't think guys can use the pinpoint to do this because we have our own.
Yeah,
It's our own version that we have here.
that's right.
And yeah. Okay, so yeah, let me know what you. I'm gonna try to make a bigger hole for V1 and see how it goes. I want to mention that if we use a 4-shank, so we have to change everything on the, not everything, but we have to change things on the rig, which is also maybe a bit more time consuming, and testing, and then see the output, how we can deal with like different probe of different types. But like I can try this and then let you know. And then please let me know if you have any questions, suggestion, ideas. If you're happy with that, if you're not, if you want something else, please just reach to me.
So is the idea that then with post hoc histology, the locations will be confirmed?
Yeah,
Like
of
people.
course. Yeah, of course. Once the experiment is finished, so after the 4 days of recording, the mouse would be perfused in the next morning, and then it will be imaged after that. Then we do on parallel, we do the spike sorting, and using together spike sorting and anatomy, we can now look at the areas and make the limitation of each borders basically on a software called IBL, from IBL, sorry. So yeah, it is of course confirmed by anatomy. Yes.
And these are the regular NeuroPixels probes or the new ultra probes?
No, that's the regular, the one, NP1. Yeah.
Okay. If there are no more questions, maybe thank you, Severin. This was fantastic.
Sure.
Maybe Nicholas is here. Are you there?
Can you hear me?
Yes.
Yes.
I
I will
please start.
Oh, okay. Yes. So I was focused on the statistical power analysis. I am still undertaking an analysis of the oddball block to see how it is that deviant angles will impact synaptic responses over the course of the odd block. That is over the course of time. So that analysis is still underway. So this presentation is just focusing on the work I'm doing towards statistical power analysis, where my focus is to eventually make use of a simulation to perform a statistical power analysis and incorporate uncertainty about orientation tuning vectors into that simulation. Now, what do I mean by that? I mean that in previous analysis that I've shown in our last meeting and also on the discussion threads, I made a comparison of orientation tuning vectors between the pre and the post block. But I think an important question to ask is how reliable is the computation of those orientation tuning vectors? Because when I performed that analysis, I, in a very ad hoc way, had simply filtered out those ROIs that did not exhibit clear orientation tuning, that did not seem to be clearly preferring one angle or multiple angles. So part of the purpose of this analysis is to really try to understand more deeply which ROIs are exhibiting what is the distribution of those ROIs that are exhibiting clear orientation tuning? Because it seems like if we're going to compare orientation tuning vectors at all between pre and post block, then we need to identify or have some sense of which ROIs are exhibiting clear orientation tuning and what is happening to the ROIs after the presentation in odd block, for instance. Are they exhibiting more reliable orientation tuning after the presentation of the odd block compared to the pre-block? So that was an assumption I never really looked at in my previous analysis, so that's the focus here. And this is supposed to be something like a preliminary to a simulation that would actually look at statistical power. Okay. So with that said,
Nicholas?
yes.
May you able to go full screen so that we can see?
Yes. Yeah.
Thank you.
Of course. So this is just a outline of the steps I've taken to approach that question. Where what I do is I'll show figures. Maybe this will better describe what it is I'm talking about. Before continuing on my analysis, I wanted to see if ROI responses to gradings followed some kind of normal distribution. So what I did was I took the mean response of each ROI for 0.5 seconds after a stimulus presentation, which could include the 0-degree stimulus presentation, the 45-degree, and so on. And I took the mean response for that ROI to that stimulus presentation, and I calculated the residuals. So we can get a sense of how variable is the response of each ROI to a given stimulus presentation. And just for the purposes of visualization, I took all of these residuals and I put them all into one big histogram. So we can see here is that the residuals don't exactly follow a normal distribution. There seems to be some skewness. That is, at certain points, the ROI is tending to respond. Well, it exhibits skewness, and I think that would be relevant to any future statistical analysis. Yeah, and this is we see something similar for the post block, similar skewness in the residuals of the responsiveness of each ROI. And I think it's important to consider this, especially when we're going to be performing statistical tests later on that may require assumptions of normality. So in addition to this, I computed essentially a metric to evaluate how consistent orientation tuning vectors are across blocks. So what I did was I randomly split the trials within a block into in this case, I randomly split into 25 times into 2 subsets. And I computed from these subsets the orientation tuning vectors, and I computed the Pearson correlation between them. So essentially, given 25 random splits, computing the orientation tuning vector between these subsets, what is the Pearson correlation between them? And I take that to be a metric of how reliable an orientation tuning vector is, say, within a given block. And it seems like when I computed this metric for the post block, I saw more consistent tuning as opposed to the pre-block, where if I were to take 2 random subsets, calculate the orientation tuning vector, it seemed like there were big differences between the orientation tuning vectors, or at least this is what this figure would suggest. And this is the same figure, but presented in a box plot format. So in addition to that, I computed something called the Rayleigh vector strength, which is a metric of how tightly clustered ROI's responses are around a single orientation. And what this suggests is that if the ROI is very sharply tuned, it tends to exhibit more reliable tuning. Now, finally, I computed this ANOVA just to see between the pre and the post blocks how many ROIs are exhibiting orientation tuning that exhibits well, that rejects this null hypothesis, which is that all iteration means are equal. And what we're seeing is that in the post block, we're seeing more ROIs that are exhibiting at least one orientation that elicits a different mean response, at least when evaluated with this ANOVA p-value. I did not perform any correction for p-value inflation, which is an important point. So I think that, yes, and to continue, here you see a scatter plot looking at, on the one hand, this split half reliability metric, which is a measure of the correlation, of the Pearson correlation between orientation tuning vectors after performing the methodology I described earlier, and the ANOVA p-value. And what this suggests is that as the orientation tuning vector becomes more reliable in a given block, as the Pearson R correlation is greater between these random halves, the number as our reliability increases, we're seeing more ROIs that exhibit significant tuning for one or another orientation. That is, they're exhibiting a lower p-value with respect to this ANOVA test, which makes sense. So yeah, so all this is supposed to be a very, very preliminary analysis in preparation for statistical power analysis to be done later. And I'll also include all the code that I use to generate these figures in a Google Colab that I'll include in my GitHub discussion thread.
And Nikos, I have a question, which I think maybe relate to what Sarah asked. She asked, I'm not sure why one will need to use test assuming normality. I think some of your analysis still hold, but you could run tests that do not assume that, right?
That's right. I could run non-parametric tests. That's correct. Yeah.
And is there a reason why to choose Boost? Or?
Occasionally, I saw in the analysis of other presenters that they were occasionally using t-tests, and t-tests require an assumption of normality.
Yes.
So I think that we should be cautious when running t-tests and rely more on non-parametric tests, especially since we're seeing this non-normality, at least with respect to these residuals.
Yes.
Yeah.
And your analysis support that the ALBA block is having an effect on the orientation tuning so far. Is that fair?
I think it suggests. I think that the figures suggest that may be the case. Whether that is indeed the case, I think we would need to compare this to a control experiment, like the kind that you're intending on implementing. But I think it would suggest that. I think there's perhaps a little bit more work to be done to ensure that the patterns we're seeing in these figures are not due to artifacts, like for instance, photo bleaching. But I think that this figure suggests that may not be the case, since it seems like if this test is reliable and it passes, the effect of p-value inflation, I think it suggests that we're seeing stronger tuning after the presentation of the oddball block, and that is tuning that exhibits that is ROIs that exhibit clear tuning preferences, and that these ROIs tend to retain that tuning in the post block. That is, they exhibit more reliable tuning. They're not, if we're taking a random subset of trials from the post block, we're not going to see different kinds of tuning. Yeah. So I think if I were to summarize, like, what is the main takeaway from this, I would say that with the oddball block, after the oddball block, we're seeing more reliable tuning, and we're seeing clear orientation tuning. So I think what this implies is that if you were to compare the pre-block to the post-block, you cannot assume that an ROI that exhibits clear tuning in the post-block also exhibits clear tuning in the pre-block. That's what this analysis suggests.
So as a vision scientist, I find this very interesting. I also have a hypothesis what's going on here that could be immediately be tested. So the oddball block is, while it is about oddballs and predictive coding, it's also, what it really does is just shows the orientation 0 an enormous amount of time, right? And so what classical work in the primate would suggest is that should sharpen orientation tuning with some kind of adaptation. Adaptation is such a poor term because there's at least 15 different processes that are all called adaptation, right? But so what I'm suggesting is you could do an analysis where you look at the diminishment, the reduction of variance. This is what you call increased reliability, right? So it seems that the variance goes down in the post-oddball block. Does it make sense? There's less noise. The neurons are more consistently, reliably indicating that they prefer a certain orientation. Is that correct?
Can you repeat your last question?
So the neurons are more reliably, consistently indicating which orientation they prefer, right? So there's less noise, less variance, less variability.
Yes.
Okay,
right.
so my prediction would be that if you look at how this reduction in variance occurs as a function of orientation, you should also see an effect.
I see.
It should not be uniform. So if you yeah. And so for that, we don't need any other controls. If you see something there, basically you have a paper that could be published, because now you're going directly after this mechanistic hypothesis that showing so many zero orientation changes these synapses because they're bombarded with the same stimulus, and even perceptually that changes how you see line orientations.
Kareem? Okay. So this is interesting. I echo what Alex said. The one thing that I'm unclear on is when you calculate the differences as a measure differences in the amount of tune, the mean, right? So less noise in post block means that the tuning is much sharper. Does that apply to all ROIs equally likely, or did you come across a subset of ROIs that their tuning was there in the pre-block, but wasn't strong enough and got strengthened, or maybe didn't get as stronger in the post-block as others in the pre-block that were originally strong to begin with?
I see. I did not track what happened to individual ROIs. So this analysis does not condition. This analysis does not consider what ROIs were like in the pre-block compared to the post-block. Since it sounds like how I understand is what you're asking is, if say an ROI in the pre-block exhibited very reliable tuning,
Yes.
will it exhibit very reliable tuning in the post block as well?
Yes, to me,
Uh,
I look
yeah.
at this as a signal to noise ratio, right? So there are broad tuning, there are sharp tuning. Not all ROIs in the pre-block would be equal in their tuning, right? Now the question is, if we broadly categorize these ROIs in the pre-block as very sharply tuned and broadly tuned, what amount of change or reliability is maintained or boosted in the post-block, given these two categories to begin with?
Yeah, I think that would be a good follow-up analysis. That I think that would be a good follow-up analysis. That may have relevancy for a statistical power analysis. But this plot that I'm showing here, I think touches on what you're talking about, where the vector strength is a measure of how tightly clustered the ROI's response is around a single orientation. But of
So
course,
in
if
this
this is
case, all these rightmost dots, all these rightmost ROIs, are these not as sharply tuned, or are they sharply tuned?
if they're higher up on the y-axis, they're more
Mhm.
sharply tuned.
Okay.
If they're more to the right, that is higher on the x-axis, they exhibit more reliable tuning in their given block.
Okay.
So the more reliable tuning the ROI exhibits, it also tends to be more tightly clustered around a single orientation. But this is not looking at the difference within individual ROIs, which I think would be a very interesting follow-up. But yes, I think to respond to Dr. Meyer's point, I think that it does make sense to me that if you were to expose the mouse to, say, the 0-degree orientation a lot during the oddball block, that you would expect that perhaps these changes are because of that. And that if we were to look at the individual ROIs and how they've changed their orientation tuning, we will find that perhaps they've changed their orientation tuning towards the 0-degree more because of that odd block. Although I think that given my previous analysis that I presented 2 weeks ago, running a PCA, comparing the orientation tunings between the pre and the post block, I think that perhaps the story is a little bit more complicated than that, and it could be that the oddball block, even though you're presenting the 0-degree stimulus a lot, in addition to the 45 and the 90-degree, it could be that the kind of change that oddball block induces is more complex than simply inducing an ROI to prefer one orientation or another. And I recently updated my figures for that analysis in the GitHub thread for meeting 617, since I had corrected for a bug that that was pointed out during a last meeting. And those figures seem to suggest that those changes are a little bit more complex. So perhaps the increase in reliability here and perhaps the ANOVA test results are due to these complex changes that were indicated or suggested by my PCA analysis.
Now, does the experiment have a block where we can test a washout of this effect? So in other words, in the post block, whatever reliability is increased or decreased, does that get sustained or continue on, or does it return back to pre-block reliability after some time?
I mean,
don't have a
this one
washout.
analysis I did is that where you see that the just the overall activity level for units that have been tuned or responsive to, for example, 0-degree, the standard, they get heavily depressed, and this depression continues like minutes into the post block. And those in these analyses we do currently would appear as being probably, I would say, less reliable because the overall response is depressed. And then there are others that haven't been responsive to 0 degrees from, for example, in the beginning, but then they become responsive in the end. And those probably, yeah, will be more reliable. But I guess that we have to be cautious with these adaptation effects going like overshadowing some of these effects in the post block.
I want to be mindful of the time. Lucas, I feel like maybe, I don't know if you're available next week, but do you feel you have time to present that next week?
Sure, yeah.
Yes, that's a yes or no?
Yes.
Okay. Okay, fantastic. So when we have the time to discuss it, thank you, Nicholas, so much. This is really insightful. I do want to share my screen quickly before we part. Okay. So this stimulus design here is something we've talked about for multiple sessions, and we've iterated through a couple designs. So I think now it includes a longer orientation 1 block to accommodate some of the point that Kareem and Lucas described, and it present 2 standard oddball blocks that would bias different orientations. And I think we need to move forward because some of the experiment can be done now. And so I would like us to run some experiments this week with that design. It's ready in Bonsai, and so for us to execute, it's just a matter of doing it. Even up the analysis that I've been doing, it feels to me like this is adding value to everyone's to run this experiments. If that's not the case, please feel free to raise your voice. Okay.
I think this is a really great design. The only thing is, when we were discussing this, I misunderstood a bit the purpose, of adding the extra length to the orientation 1 block.
Yeah.
And so I think adding it, if we want to control, for example, for habituation or adaptation effects, and we really want to ensure that the responses within the orientation block are non-transient, I feel like maybe we could split that extra time and add just like 1.5 minutes or 2 minutes to each of the orientation blocks, because they are also like these after adaptation effects after the oddball blocks that can bias our results that we
Are you asking for gray screen?
No. Maybe you can quickly share my screen.
Yes.
I have one image where show this. So what I mean is adding essentially. Can you see it?
Yes.
Okay, just adding 1.5 minutes to each of the orientation blocks, so that we have a bit of a period that we can in the end cut out of the analysis to ensure that there's not like adaptation from the oddball block spilling over into the orientation block.
So what is in this block?
Which one? This extended orientation block. So it can be just random orientations, and we should just make sure that we have the 30 trials for each.
Oh, so you just want a few more trials than 30?
Right. Just adding yeah, like about what amounts to 1.5 minutes or so.
But during boost 1.5 minutes, this is just shuffle drifting gratings?
Exactly. It's the same stimuli we show in these blocks, just extended a bit.
I see. I
so
see.
that we
Okay,
have-
so that's
We have
easy to
some
do.
space to cut out stuff if we see it's non-transient, because it's just the analysis we were talking about.
Yes.
Because there
Yes.
seem to be these transits not only at the first block, but also the second one. So it might make sense to have this
Okay.
bit of a buffer here.
Yeah, that makes sense. That's easy to do. Okay, so I'll edit the design and then deploy that. We are talking about doing the experiment tomorrow, so I feel that's why I feel like, and we can iterate forever, and then but I feel like there's a trade-off at this point where getting the data earlier will be more helpful than iterating more. So if I'm can make this modification, Lucas, and then start.
Yeah,
Okay,
great.
sounds good. The other thing is next week, I think so. Lucas, you'll be presenting. I would like to lead a discussion on the over designs, the over session design. So that's going to take a big part of the session. So we'll discuss the session 1, 2, 3, and so on. And the other point is I'm going to be away for the second half of July. And so I feel like this meeting can continue after that, but maybe we need a lead. And so if someone here wants to do that, I'm happy. But if you want to continue discussing analysis, you probably, I won't be able to monitor that. So either we just cancel the meeting while I'm away, or someone lead it. Are there any preferences?
Well, I suggest we take that time to try to consolidate the analysis, the different pieces of analysis that people have done.
Okay.
Because I think there's quite a bit to digest. So we can better refine if the experimental design needs to be still refined. So maybe we should take that time off as a group and then reconvene again after you're back.
Okay. Everybody's on agreement there?
Sounds good, yeah.
Okay. But we meet next week to discuss the new sessions, regardless.
Yep.
Any
is the sensory motor component going to be part of that discussion?
Yes.
Okay, great. Thanks.
Any other questions? Well, thanks everyone. It was fantastic.
Thank you.
Thank you.